we've been looking at simplifying our trig expressions, and we looked at some kind of basic examples the first day, and then we got a little bit more complicated with it, and now we're going to look at factoring them. Alright, so we did look at one example where we had a fraction, but we didn't start with a fraction. Okay, so in this case, we're actually starting with something that's a fraction. So what do we need to do in order to be able to add and subtract things? That are fractions. Correct. So what do we need to multiply the first one by? Or like, what is it missing? The sign. So I have to multiply by sine over sine. Why is my second one missing? Yep. So again, we have to multiply that to the top and the bottom. And recall, we talked about that. Remember, we have to multiply it to the top and the bottom because we don't want to change the overall value of it. But if I do it to both of them, then we're technically just multiplying by 1. So, what are we left with on top? Here. Sine squared. Okay. Plus you. If we distribute this, what are we going to get? So cosine times 1 gives us cosine plus a cosine times a cosine is cosine squared of theta. And then our bottom, we're just going to go ahead and leave in factored form. So we have sine of theta times 1 plus cosine of theta. Now, what do we notice next? Do we have anything that might be helpful in our numerator? And a... Yeah, so notice that we can rewrite addition or subtraction really to be in whatever order we want. So now, what is sine squared plus cosine squared? One. Using our what? The Pythagorean identity. So notice now we have 1 plus cosine of theta divided by sine of theta times 1 plus cosine of theta. So notice that we performed the addition by combining them. So that was the first part that it said. And then it asked us to simplify. So that's why we then had to start looking at, are there any things that we can use our identities for? Okay, now, is there anything that I can reduce out? Well, it's going to reduce. Okay, so what are we left with on top? Just 1. And then on bottom, we just have a sine of theta. And what does 1 divided by sine of theta equal? Yeah. So that would be our final answer. Yay. Which is pretty simplified. To end up with just one trig function when we started with 2 separate fractions. Such a nice result. What questions do we have there? So this one wasn't quite factoring, but it was multiplying. So figuring out what we need to multiply each of our fractions by in order to add or subtract. Alright. So this one asks us to factor. What do we have here? What's our first expression? Secant squared. Alright, what's our second expression? -1. Alright, it asks us to factor that. Agreed? We have a binomial. So let's go back to the beginning of the year when we talked about factoring. what are our two options when we have a binomial? Or sorry, there's technically three options. One we already looked at. It's to factor out the what? Greatest common factor. Is there a greatest common factor on either one of those? Okay. So the next two are if we have something that is in a special form. The two forms that we looked at were the difference of squares or the difference of cubes. Yes? So notice, is that expression in that form? So a squared minus b squared. Yeah, so notice that my a is going to be my secant, yes, and my b is going to be my 1. And if we didn't remember what our difference of squares formula is, what does a squared minus b squared factor to? Times? Yep. So we're going to get something similar here. So my a, like we said, is our secant. Our b is our 1. So we get secant minus 1 times secant plus 1. And again, that's what our directions said to do. They just said to factor it, so that's what I did. I'm done. So again, we always want to read our directions as to what the question is asking us to do. Did it ask us to simplify? Did it ask us to get rid of the fractions? Did it ask us to just factor? Because that'll help you figure out like how far you need to go or where you can be done with your simplifying. Yes? Okay. So this is a good reminder that all of our like rules and formulas still apply. Okay? So we can still use all of those formulas or techniques. Just because we have trig functions now, they are still going to work. So what do we have here? How many terms do we have? 3, okay. Which is a what? A trinomial, okay. And again, we really only have two methods for this. First, your greatest common factor. Do those have a greatest common factor? No, but then what was our other method that we used a lot to factor our trinomials? Our AC method. So, we're going to use our AC method. And there's kind of two ways you can do it. One, you can do the AC method like with the tangents, okay? You're going to be writing tangent a lot, okay? Or, like what I think is a little bit easier is to just say, okay, let's let our b, or whatever variable you want it to be, okay, act in the place of our tangent. And then we're going to factor that, like, over off to the side. I can't put an equal sign, because obviously tangent doesn't equal b. But whatever I get for the factored form here, I can just throw my tangents back in, and it's going to be the same. Does that make sense? So just so we don't have quite as much writing to do with the tangents. So, remind me, what does our AC method tell us to do? Multiply what and C? A and C. Okay, so we get negative 12. Okay, so do we have two things that multiply together to give us a negative 12 that add together to give us a positive 1? Positive 4 and negative 3. Agreed. Okay. And then what do we do? Factor what? By grouping. Okay, so remember we group our first two together and our last two together. What do our first two have in common?
4b.
4b. So we're left with b plus 1. What does our second group have in common?
-3.
Okay, and we're left with a b plus 1 again, which is what we want. Remember, we want those parentheses to be the same because now we can factor out that b plus 1. And we're left with 4b minus 3. But remember, at the end of the day, we didn't actually have b's. We had tangents. So we're just going to rewrite that and substitute tangents in for our b's. So So this would be 4 tangent of x minus 3. And again, they just asked us to factor, so that is my answer. What questions do we have on that? Alright, continuing on. Okay, let's figure out this one. How many terms do we have? 3. Okay, so we have a trinomial again. Can I use my AC method again?
No,
Why not?
because it's two different.
So it'd be like if we had x squared minus y minus 3, right? So if we have 3 terms, so it is a trinomial, but it's not all the same variable. Does that make sense? So like, there wouldn't be a way for us to factor it as it is. Yes. However, have we been looking at any types of formulas or things that allow us to convert one trig function into another trig function? Yeah. Specifically, okay, I want to look at what we have. I have a cosecant squared and I have a cotangent. Again, we're wanting to factor using our AC method, so we want to make one of these into the other one. So really, with our cotangent, we could use our reciprocal identity and put 1 over tangent, but that doesn't help us. We can use our quotient identity and put cosine over sine, but that also doesn't help us. Okay. However, with our cosecant squared, which of our formulas might we be able to use? Yeah, so we can use that second Pythagorean. So we're going to replace our cosecant squared with a 1 plus cotangent. So are we all okay with why we chose to replace the cosecant squared? Yes? Okay. So now we just kind of want to rewrite it so it looks a little bit more like the quadratics that we're used to factoring. So we're going to leave our squared bit at the front. I have a minus cotangent of x. And then 1 minus 3 gives us a negative 2. So now again, if it's helpful, we can come over to the side and we can think about if I had b squared minus b minus 2. So I don't have to use like my full AC method this time because our leading coefficient is 1. So we can just kind of think what 2 things multiply together to give us negative 2 that add together to give us negative 1. So what are your factors of 2? 1 and 2. Okay. One of them's going to have to be negative, right? If I end up with a negative. And if I have a negative here in the middle, then it has to be the bigger one, right? So we would get b minus 2 times b plus 1. Yes? Do we all vaguely remember doing that? Which means that this is going to factor, again, just replacing my b's back with my cotangents. We have a cotangent of x minus 2 times a cotangent of x plus 1. That's my answer. Again, still all the same techniques that we've used in the past. It's just now we're throwing in some trig functions. Alright, so let's look at one last one, I think. Okay, so we want to factor, and I'm going to say, and simplify this. Because the whole reason why we want to factor is, one, we're in our next unit, we're going to have to use factoring to solve some stuff, but also because we want to use it to be able to help us simplify in some cases. And we've kind of looked at one like this before. What type of expression do right? Because terms are separated by addition and subtraction. So we really only have two. So we have a binomial. Yes? So what are our two methods that we can use?
Difference of squares.
Difference of squares or forgot the first one. Greatest common factor. Yeah? Which you technically could use a difference of squares here because we could say that this is sine times cosecant like quantity squared. Does that make sense? And we could factor it that way. But do we notice anything else? Do we have a greatest common factor here? What's our greatest common factor? Sine squared. Alright, so if we factor out a sine squared, what are we left with? Okay. Now, if it just asks us to factor, then yes, that would be our final answer. Okay, but I said to let's say and to simplify it. So, what do we notice that we have there? We have a bunch of squared, so what are we probably going to use? One of our Pythagorean identities. Okay. Now notice, usually we at least want there to be two of the functions, right, that are in Pythagorean identity, or one of the functions and a 1. Okay, because technically I could use my Pythagorean identity for the sine, but notice on the inside we have a cosecant and a 1 already. Does that make sense? So that's why we're probably going to choose that one to go ahead and use our Pythagorean identity with. So what is our Pythagorean identity that has the cosecant with it? Yes, what is it though? Yeah. So 1 plus cotangent squared of x equals the squared cosecant squared of x, yes? But how would I get my cosecant squared and my 1 on the same side? Subtract the 1, so we get cotangent squared equals cosecant squared of x minus 1. Does that look vaguely familiar? Hopefully so. That's what we have in our parentheses, yeah? So what can we substitute in for our parentheses then? Okay. Can we simplify that any further? Yeah. What do we know about cotangent? Agreed. And because my cotangent is squared, both the cosine and the sine have to be squared. So then what are we going to be left with? Cosine squared. Yes? We okay with that? Now, I think I've said before that sometimes there are multiple ways to get to the same answer. So let us say that we didn't see that we had a greatest common factor here. And instead we wanted to use our difference of squares formula. Okay. So remember, like I said, this could technically be sine of x times cosecant of x quantity squared minus sine squared of x. Agreed? Yes? So, we would get, this is going to be my A, this is going to be my B, so we would get sine of x cosecant of x minus sine of x times sine of x cosecant of x plus sine of x. Agreed? Everybody okay with that? And again, we're starting with that because it did ask us to factor first. It just asked us to simplify, then we wouldn't have necessarily had to factor first. Now, what do we notice about our sine and our cosecant? What's the word that we use instead of opposite? Like which identity? Yeah, they're reciprocal. So when I multiply them together, what are we going to get? Not 0, right? This would be like 1 over sine. So my sines would reduce, but I'm still left with a 1. So I would have 1 minus sine of x times 1 plus sine of x. Alright, okay with that? And then notice that if I were to go ahead and multiply this out, I would get 1. Notice that we're going to get a positive sine of x and a negative sine of x, so those are going to go away. So I get 1 minus sine squared of x. Now, what does that look pretty close to? Yeah, still our Pythagorean identity, but this time it is our sine squared plus cosine squared equals 1. So again, notice that if I want to move my sine to the same side as my 1, I would subtract. So then what does that end up equaling? Cosine squared. Which is what we got on the last one, yeah? So we got to the same answer. It's not like one of those was more right than the other. It's just they're different, okay? As long as you're using your identities correctly, okay, both of those would be right, which is why it's going to be important on your homework quizzes, and on your tests that you write out your steps and you write them out clearly. If I can't tell what you're doing to get from step to step, I can't grade it. Does that make sense? Because I try and grade as much of your free response as possible, meaning that like even if I ended up with, say, like a tangent squared of x there or something like that, I would still try and grade as much of your steps as possible and give you partial credit. But if I can't read it, or like your first step is over here, but then your second step is over here, and your third step is down here, like draw arrows or circles or something for me. That way I know like what your thinking was. So that's easier for me to grade. Questions on any of that? Alright, that's all we got.